here at Caltech, doing some very early work on the SEDs of disk around P-Tauri stars.
It's so old. It's so old.
It's not that old. And then he moved to the Institute for Grand Study, where he stayed for exactly 366 days before moving to his current position at UC Berkeley, where he has been there ever since. Right? And so Eugene's going to talk to us today a little about accretion protoplanetary disks.
Thanks a lot, Bill. It's a pleasure to be here. Thanks for the invitation. All my visits to CITA have been therapeutic, and this one is no exception. It's really nice to get away and talk about science.
And see some real snow.
And see some real snow. That's part of the excitement. So my topic today is accretion in disks, how disks transport angular momentum outwards and mass inwards. It's hard to think of a question that's more basic to our understanding of star and planet formation. I mean, there are the observations themselves, which demand that material fall from the disk onto the central star. There are these jets that are, as far as we can tell, powered by disk accretion. But even apart from the observations, there are all the implications of disk viscosity for planet-disk interactions, right? The degree to which the disk is turbulent, how it redistributes its surface density, all of these factors come into play in deciding how planets migrate and what their eccentricity and inclination evolution is. So it's hard to think of a bigger question and one which has resisted a consensus understanding for so long. So I'll present a progress report today, but one which I find fairly encouraging. Okay, this is work. The work that I'll be presenting was done in collaboration with a graduate student in the physics program at Berkeley, Daniel Perez-Becker, who's been extremely useful. Okay, so here are the observations. It's undeniable that pre-main sequence stars accrete because we see tremendous amounts of radiation emitted in excess. So all of this UV radiation emitted in excess of the stellar photosphere. So all of that excess radiation comes from material that's shock-heated as it crashes down upon the stellar surface. And it's from observations like these we can set this continuum excess luminosity, Gm m dot over r, to infer mass accretion rates that are plotted here. So m dot versus stellar mass. And for solar type young stars having ages of about 1 million years or so, the median accretion rate, the target, is about 10 to the minus 8 solar masses per year. So that's what we would like to explain. Recently, I attended a conference in Ringberg on transport processes in disks, and one of the topics was, to what extent should we believe these accretion rates that are inferred? And the gold standard for inferring an m dot is by using the continuum UV excess, as I've just described. Even that gold standard is uncertain to factors of 3 plus or minus. It's the usual uncertainties in astronomy. The uncertainties to the distance, extinction corrections, the mass and the radius of the objects that are inferred from pre-main sequence tracks. All of these uncertainties gives rise to plus or minus a factor of 3 for any given system. That's the best you can do. Nevertheless, despite these uncertainties, it's still pretty convincing to most people that there is a trend in m dot with increasing stellar mass. Can't quite pin down the slope, but for sure, higher mass stars accrete at higher rates. So a subset of the...
Sorry, can you just,
sure.
just to expand on that? So
Yeah.
if you were to multiply the current age times the m dot and compare to m, how's that product? That product is going down with mass?
So the disk masses, if you do it just for solar type stars, you get fairly good agreement, meaning m dot times TH, 10 to the minus 8 solar masses per year, 10 to the 6 for the age, that's 10 to the minus 2 solar masses for the disk. And that's squarely in the middle of the range of disk masses inferred based on dust continuum measurements, which range from 10 to the minus 3 to 10 to the minus 1 solar masses. Now, I think your question is more about the trend with stellar mass, the disk mass versus stellar mass, and I don't have great data on that, but my understanding, the best person to ask would actually be Ray J. I'd be interested to know brown dwarf mass disk masses, are they lower than solar type stars? And my recollection is the answer is yes, but I'm not sure if there's really any great millimeter wave data to look out for. But for solar type stars, it works out just fine. Okay, a subset of these pre-main sequence stars that I want to highlight for this talk are these transitional disks. They're called transitional because we think they are making the transition from being entirely optically thick to entirely optically thin. If they're entirely optically thin, they're called Juvie disks. These are disks that are in between, and they're identified by virtue of their spectral energy distribution. So here are two examples, and what's plotted in green is not the SED of a transitional disk, it's the SED of a typical medium, in fact, T-Tauri star. Right? And it's fairly flat in lambda F lambda or mu F mu. And the flatness of that spectrum is a consequence of stellar reprocessing. So it's just a star, it heats the dust of the disk, it re-radiates that energy at infrared wavelengths, and the spectrum turns out to be fairly flat. These systems, the transitional disks, are not flat. They have a deficit of emission at mid-infrared wavelengths. So 10 microns emission, 10 microns wavelength. This red trace is from Spitzer, and they sit below this typical conventional T-Tauri spectrum. And that deficit of emission is translated, is interpreted in terms of the deficit of material. That is, these disks have holes. The holes range in size from a few AU to dozens of AU. Here's a schematic for TW Hydra where the hole size is inferred based on the SED to be a few AU, and inside the hole, the material is optically thin, so optical depth at 10 microns measured in a few percent, but just outside, it's orders of magnitude larger. We should keep in mind, though, that these numbers are fairly model dependent, right, because they're based on SED modeling. So there are degeneracies in these model fits. But it's fair to say it's optically thick on the outside and quite a bit optically thinner on the inside.
So that feature 10 microns is that a silicate?
Yeah, that's the silicate SIO stretch.
It's the emission that
Exactly. That's referring to all the dust that's sprinkled inside the inner disk. So that's one of my points on the next slide, which is that even though it's optically thin, it's not zero. Right? There's still a little bit of fluff inside. Now this interpretation that's based on the SED in several instances has been vindicated by direct imaging. So here's an image of one of these guys. So a Herbig transitional system. And this is an 850 microns wavelength of map. And here you see these warm dust grains in a ring whose projected radius is about 40 AUs. So just in passing, I won't go into any detail about this at all, but notice that the ring is not all the way around, it's bumpy. It's also offset relative to the position of the central star. And all these non-axis symmetries get people excited because they think, oh, they might reflect gravitational forcing from planets that are embedded inside. So, as I was just saying, it's important to appreciate that these holes are not completely empty. I've just pointed out the fact that the optical depth is not zero in many, but not all sources. Many of them, they have a mild near-infrared excess, a sprinkling of dust inside. We also know that the hole is not empty because we see their central stars accreting. And they're accreting at rates that are comparable to those of disks without holes. So here's an early compilation by Joe Nagita. The dashed histogram are the accretion rates for transitional systems, and solid histogram is the accretion rates for non-transitional systems. And it's argued in the paper that this is significant, that it might be that these accretion rates for the ones with holes are a little bit lower, maybe a tenth the accretion rates of conventional sources, but they're quite comparable. So we know that material is falling down over the star, and that gas must originate from inside the hole. So we know that the holes are filled with accreting gas. We also know that the holes are filled with accreting gas because we can see the gas directly, but not terribly well. So you can see these beautiful row vibrational emission lines from a CO at wavelengths of 4 to 5 microns, right? For both TW Hydra and GMRI, you see coming from CO, that's warm, a few hundred Kelvin. Unfortunately, CO is very easily optically thick. So if you want to translate this CO detection into a surface density at H2, the bounds you can place aren't super interesting. The bound is a 1/10 of a gram per square centimeter at a fraction of an AU. That's where the material is hot enough to radiate in these lines. So a 1/10 of a gram per square centimeter means a heck of a lot compared to the thousands of grams per square centimeter that you might expect from the minimum mass limit, for example. Yeah, but there it is. You see, there is gas inside the hole. If I had to summarize all of these observations, this is the question that I keep asking myself over and over. How can it be that these disks have orders of magnitude smaller optical depth in their innermost regions and yet still have the same accretion rates that are observed for disks without holes? How can you have your cake and eat it too? And there are many theories proposed in the literature. I'm going to discuss or bring up just two, which I think are the most reasonable. The first one is brain growth. You take the same amount of solids and you just allow it to coagulate into bigger particles. Having smaller surface area for the mass, you make the disk more transparent. The other idea is clearing by a companion. So gravitational torques exerted by some companion to the star that repels material away from itself, and in this way it clears out a hole. Now we know that the idea of clearing must be right for Koku Tau 4 because we see the companion. This was really great work by Mike Ireland and Adam Krauss using tech-adaptive optics. In the one case of Koku Tau 4, they saw a central binary with its nearly equal mass. They saw it in the near infrared. The projected separation of the binary is 8 AU, comparable to the whole radius of 10 AU inferred from the SED. Here's a really early simulation by Pavel Arsimovich. It's an oldie but a goodie, and it demonstrates exactly what Koku Tau 4 is probably like. So here's a central binary. This is an SPH simulation, and here's a central binary clearing out all of this material. There's not a single SPH particle that can penetrate inside this zone. Right? And this is consistent with Koku Tau 4, whose hole is remarkably clean. So the optical depth at 10 microns for this particular source is unmeasurably small. There is no silicon emission line at 10 microns. The mass accretion rate is also unmeasurably small. And there's no CO gas to speak of. Last time I talked to Jeff Blake and Colette Salad, they said, like, we don't see anything. So in the one case of Koku Tau 4, we know clearing by a companion, in this case a stellar companion, is the right answer. But this is the minority source among transitional systems. Most of them are not like this. The holes are not so clean. The stellar binary can still work because the edge of the hole can be leaky. Right? Mass can still accrete from the edge of the hole onto the central binary, whether it can accrete or not. Some complicated function of the viscosity of the disk, the pressure of the disk, the properties of the binary, the eccentricity of the binary, the exact mass ratio. And there is a large region of parameter space which permits streams of material to accrete onto the central binary, leaving, and at the same time, leaving a fairly clean hole to either side. So this way you can have your cake.
You just need a fairly high viscosity to prevent the picture from the previous one.
Yeah, that's right. No, it's in this parameter space of viscosity, pressure, and the properties of the binary. I forget the exact alpha value they used, but they were exploring some range. This is one way to do it. If you want to use lower mass companions, obviously the lower the mass, the more companions you need, right? Because if you have a Jupiter mass planet, the gap that it carves out is too narrow to explain these extensive AU size holes, 10 AU size holes that are observed from the SED. So you have multiple low mass companions. And this was an idea that Yang and I were batting around last year in Beijing. And little did we know, as we were talking about it, Xiao Guanzhu at the same time was simulating it. And he came out with this paper just recently. So a simulation in which he placed four planets inside the hole, surrounded by a viscous accretion disk, just an alpha disk, and sees what happens. So on the left-hand side is plotted surface density versus radius. These are four different models, and the four different models differ according to what's assumed about the accretion efficiency for the planet, right? Every time this material comes by the planet, you have a choice to make. How much of the material is eaten by the planet, and how much of it is just torqued away. Now that accretion efficiency, estimating it from first principles has been hard. It depends on the thermodynamics, how effectively the material can cool so that it lands on the planet. So rather than dealing with that messy microphysics, these authors just assume a boundary condition for their single cell. They take some fraction of the material within a Hill sphere of the planet, and they allow it to creep onto their single cell within a dynamical time. And that fraction varies from model to model. So in this case, there is no accretion, but in this case, there is the most efficient accretion onto the individual planets. So not surprisingly, where it's most efficient to carve out the biggest hole, because all the material just being eaten out by the planets. The model they like to point out, Juvie et al. Like to point out, is this one, this dotted line here. And you can see the four planets, right, where they're positioned. They're positioned near the trough. So here, 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 here. It carves out a gap that's several AU in size. They like this model because when they plot the accretion rate onto the star, the accretion rate onto the star is within the bounds of observation. So this model here corresponds to this model here. So m dot versus time. And the m dot versus time, over 1 million years, it's between 10 to the minus 8 and 10 to the minus 9 solar masses, which is in the right ballpark. Now, you take a look at this model, the surface density depression is not, it's only an order of magnitude, even a little less on the outer edge. On the inner edge, they're depressing the surface density by something like a factor of 30. This is a little bit too low compared to the SE models, which demand closer to factors of 100 to 1,000 suppression in the optical depth. So these authors argue that, well, maybe this is what's going on, but at the same time, we really need grain growth at the same time to recover an extra order of magnitude or so to make this really optically thin. So this is where things stand. It's still early days. I'd like to explore things like eccentricity, brown dwarf masses, but companions and grain growth are reasonable things to think about. And if you go to enough of these conferences like Ringberg on this subject, you'll get the impression that planets can explain everything. That's everyone's favorite answer. But for transitional distance, well, it's clearly not the case, right? Because the planets are inside the hole. And while they can shuffle material along one planet to the other and speed up the accretion flow, and this way reduce the surface density just by continuity, they can speed up the accretion flow, but they can't explain the accretion in the first place, right? You still need a reservoir of material, which is feeding the whole process. That is the outer disk. You still need to explain why it is that the outer disk is leaking onto the inner system in the first place. And that's my talk. So how is it that this outer material can bleed onto the central object? And the mechanism that I'd like to worry about is the MRI. Everyone knows about the MRI. It's a powerful linear instability. You take a disk, you thread it with a magnetic field, it ties together fluid parcels. The parcels on the inner radii rotate faster than the ones on the outer radii. Angular momentum is transferred from the inner disk to the outer disk, and mass goes inward. So here's a movie by John Hawley of this process. You can see that the MRI excites turbulence, which transports matter inwards at a very healthy rate. The MRI works. It works like a charm, but it only works where it can in protoplanetary disks, which are on the whole too cold and too dusty to support magnetic activity. So there are a couple of requirements, at least 2 requirements that need to be satisfied before the MRI can take hold. The first is that you better freeze your plasma into the field. The usual criterion for this is the Reynolds number, magnetic Reynolds number. I'll cheat a little bit, and instead of using the Alfvén length scales, I'll use just the sound speed and the gas scale height. It's easier to do it, it's more convenient to do it this way, because you don't need to estimate a priori the B that's in the disk. This is also the approach that was taken by Fleming. So this magnetic Reynolds number, it goes, it's inversely dependent on the magnetic diffusivity. The whole thing scales as the fractional electron density, which makes sense because it's the electrons which are the most mobile charge carriers. They're responsible for the conductivity. And it's the neutrals, the H2 molecules, that are providing all the resistance. So you like this number to be, this dimensionless number to be large. According to this simulation by Fleming, critical Reynolds numbers on the order of 1,000. It depends on the geometry of the seed field that you assume. Now this is the criteria, sorry.
So just by replacing the Alfvén criterion with the sound speed, you basically evaluating the magnetic Reynolds number as if the field is saturated and seeing improved.
That's right. That's exactly right. Because if you had done this replacement with using the B, using the Alfvén speed and the Alfvén light scale, you would get what's called the Alsacer number, and the criterion then would be 1. Which, okay, this is the criteria that most people obsess over in the literature. In fact, it's not the most important criteria in disk surface layers. I don't care how frozen your field is to the plasma, unless the plasma can talk to the neutrals. Only the plasma will get to participate in the MRI and leave the neutrals behind. And that would be a disaster, because these disks are overwhelmingly neutral. So you need to couple the neutrals to the ions. The ions carry the bulk of the momentum. In other words, you need to worry about ambipolar diffusion. You want to make sure ambipolar diffusion is not a concern. So if you're a H2 molecule, you need to collide with as many ions as possible within the dynamical time. That's the time scale over which the MRI amplifies. So that, I can define another dimensionless number. I'll call it AM for ambipolar diffusion. That collision rate between an H2 molecule and a sea of ions has to be large enough. That dimensionless collision rate has to exceed its own magic value, which according to this early simulation by Hawley and Stone was a number on the order of 100. In fact, there's more recent measurements of this by Hawley and Stone, which I'll refer to later. Okay, so this is a significant criterion for protoplanetary disks. It was recognized early on that the entire disk cannot satisfy both of those criteria. This was recognized first by Charles Gammy, who pointed out that the mid-planes were just too cold and too dusty to support magnetic activity. But the surface layers, which were exposed to some non-thermal source of ionization, could support the MRI. So active layers sandwiching the magnetic dead zone. Now, various sources of ionization have been proposed over the years. Gammy worried about cosmic rays. Since then, people are talking about X-rays. And what we've done is we've included the effects of ultraviolet. And I'll go through each of these sources and go through their relative importance. So, yeah.
On the ambipolar diffusion number,
Yeah.
why is that important? If I could completely talk from each other, why say it's the plasma participates in MRI?
Yeah.
So why is that the fact?
Oh, because the plasma carries a tiny, tiny, tiny fraction of the overall mass.
Right.
And I'll give you some numbers for how tiny. It's like 10 to minus.
So it just suppresses basically the amount of.
Yeah, reduces your accretion rate by billions. So, okay. Right, so cosmic rays. Well, it's a hard case to make for cosmic rays. It's well known, even for the Earth, that the solar wind, our little old piddling solar wind reduces the cosmic ray flux by observable amounts. Right? So, for example, this is plotting sunspot number versus time. So this is solar max, this is solar wind, solar max, solar wind. And then you plot simultaneously with it the cosmic ray flux under at two different energies. I think this is 0.1 GeV and this one's 1 GeV. And there's an anti-correlation. Every time there's solar max, there's fewer cosmic rays. So even our little solar wind, emitting at a rate of 10 to the minus 14 solar masses per year, can affect the solar wind at levels of a few percent. Think about the magnetized stellar winds from these pre-main sequence stars, emitting at rates of easily 10 to the minus 9 solar masses per year, 5 orders of magnitude larger. It's really hard to imagine galactic cosmic rays, which ordinarily would have an ionization rate of 10 to the minus 17 per second, having any effect at all in these disks. So I'm not going to focus on cosmic rays. I should point out, though, that, this is pointed out to us by the referee, that cosmic rays might still enter in from the sun, parallel to the disk of the planet. We did that estimate. He's right, he or she is right. It could be important in the outskirts of the disk, outside of 30 AU or so is our estimate. But inside, it's not a relevant ionization source.
And locally generated, locally accelerated.
So that's an interesting source of, that's an interesting source. I did an estimate. I mean, this is also uncertain, right? Because it can also be shielded by magnetic fields. But, so I did an estimate, and it was actually comparable to the ionization from X-rays. X-rays has none of these caveats. So I'll talk about X-rays from now on. But you're right. It's, high energy particles emitted by the star itself could be, maybe, comparable to the contribution from X-rays. So I'll talk about X-rays instead because I don't need to worry about shielding. Here are the observations. Rate observations at X-ray band. Chandra did a great survey of the Orion cluster. Here are the X-ray luminosities versus stellar mass. 10 to the 29, 10 to the 30, even up to 10 to the 31 ergs per second. 2 temperature plasma. There's a soft component, which is about 1 keV. There's a harder component at 3 keV. They have equal luminosities, comparable luminosities. It's the harder component that interests me more because that has greater penetrating power and gives rise to a thicker MRI active layer. What happens when an X-ray hits the disk? Well, it produces a bunch of H2+, which collides and quickly produces other ions like HCO+. Now, HCO+ and ions like it can neutralize in any number of ways. There's a fast channel, which is direct recombination with an electron, and it splits up into H and CO. This is fast because it's Coulomb focused. Now, it's possible, this was pointed out by Oppenheimer and Galgarno, that it's possible for this ion to transfer its charge to a free metal, like magnesium or iron, if there are any left around. A lot of them will be depleted onto grains, but if there are a few left over, they can transfer their charge to Mg, create Mg+, and that is generally good news for the MRI, because Mg+ tends to hang on to its charge. The only way, well, one way for it to neutralize, it can't do so dissociatively, of course, and it's got to do so by the emission of a photon, right? So Mg++ E equals Mg. Because a photon is involved, that reaction is orders of magnitude slower. So Mg+ tends to hold on to its charge, and that's good news. Unfortunately, there's bad news too, which is that Mg+ can also recombine by neutralizing on negatively charged condensates, grains. And also, I would like to add pods. Right, in any given size distribution of grains, usually, when you are lucky enough to measure it, usually the surface area of this size distribution is concentrated at the low size end, the smallest grains. They don't carry much of the mass, but they carry a lot of the surface area. So the smallest grains that I can think of that are still accessible to observation are PAHs. So those are the ones I would like to consider. So neutralization onto these negatively charged They're negatively charged, right? Because of collisional charging. You take the brain, the electron flux is greater than the ion flux because the electrons have larger speeds, because they're lighter. So all of these condensates can be negatively charged. Okay, that's in a nutshell the chemistry. A word or two about the pHs. So here they are, these sheets of hydrocarbons. If you make a big enough sheet of this, you can get a Nobel Prize. Forgetting about the hydrogen end members. Make graphene. The universe makes these in bits and chunks. You can see them in emission from young stars. They get zapped by a UV photon, and then they fluoresce in the infrared. And the fluorescent emission is from CC and CH bonds. So these emission lines from these stretching and bending modes at 6, you see here 6, 7, 8.5, 11 microns, and you can see these lines poking up. And they're all from these individual lines of these hydrocarbons. You tend to, I've seen it quoted in the literature, over half of hot pre-main sequence stars, so Herbig AEs, a large fraction of them, the majority of them, exhibit pH emission. T-Tauri stars, lower mass stars, less so. And I think that's just a detectability issue. It's because there's less UV continuum to excite the lines. So it's just harder to see in these less luminous, lower mass stars. But sometimes you can still see them. In fact, you can see them preferentially in transitional systems, because it's easier for you to detect a line poking above the continuum if the continuum was already low. And it is low for transitional systems. So they tend to be preferentially detected in transitional systems. Based upon these Spitzer spectra, so we did a literature search and we tried to estimate as best as we could the abundances of these macromolecules. Depends on the degree to which the dust is settled. We get order of magnitude estimates, a range actually, that's measured in parts per billion. So 100, 10 to the minus 11, up to about 10 to the minus 8 pHs per H2. That's already orders of magnitude smaller than the pH abundances that people infer in the diffuse ISM, where the radiation fields are a lot less. So that's the right sign at least. Stronger radiation fields, you expect the positive to be destroyed more, but they're still there, but at a lower abundance.
How is pH made? Are they made in ISM or made in source, in actual source?
That one I don't have a great feeling for. The picture I've always had in my mind, at least in disks, is that they're sputtered off grains. That X-rays or UV radiation to sputter off these molecules off of the grains. And they can recondense, and there's some cycle. Modeling this seems pretty difficult.
Is it somewhat similar to soot in the sense that it's a photochemical? If you think of it as a photochemical smog, is that reasonable way to think of it?
I think so. I really don't know the details though. I do know that the pHs that are in disks are not just the unadulterated pHs that were transported in from the diffuse ISM. These pHs have been reformed in the disk environment, and we know that for sure because the shapes of the bands look nothing like the shapes of the bands in the diffuse ISM. And moreover, the shapes of the bands in disks actually trend with spectral type of the star. So the hotter the star, you see the shapes, there's systematic trends. So there's definitely reprocessing of the pause going on locally. Yeah, that much is clear from the observations. Yeah, forward modeling it, yeah, I stay away from that. So where do I get this abundance? I get it from these observations. As best we can, translating these line fluxes into abundance measurements. So that's what we do. This is too busy, but I'll walk you through just bits of it. So look at this plot first. So XE, the electron fraction, versus pH abundance. Like this is all normalized to hydrogen, so these are fractional abundances. And just look at XE for now, which is the solid circles, this curve right here. Okay? And it's clear, as the pH abundance increases, the electron fraction goes down because all the charges are being they're recombining on these negatively charged pHs. This gray band is our best guess, our best estimate, based on the observations of what the pH abundances actually are in this surface layers.
So you're doing some chemical modeling. Got some chemical answer.
Oh yeah, that's right. It's an ionization calculation. We solved in detail, that brings me to the next plot, for the charge distribution of the various condensates. Right? So for example, these pHs that are soaking up all the charge, half of them are neutral in equilibrium. Roughly half of them are negatively charged, -1, and a very tiny fraction in equilibrium turn out to be positively charged. We worry about all these fluxes and balance all the rates. It's not hard, but we do it in detail. Okay? And for grains, which are a lot bigger, their Coulomb wells are a lot shallower, right? It's a much bigger size. It's 6 angstroms for the pH versus 1 micron. Grains are gigantic on this scale. And they can carry a lot more charge because the electrons just find it a lot easier to land on the big grain. So they have equilibrium charges that are centered at -22. So each grain, on average, has a charge of -22. We solve this distribution. Okay, so that's basically it. This plot is just trying to tell you that pHs make a difference. Even at their lower abundances relative to diffuse ISM, they can make a 2 order of magnitude difference in the ionization fraction. Okay, here's the bottom line. Here's part of the bottom line. Plotting these are rough gauges for MRI activity. Reynolds number and ambipolar number versus the surface density of the material that X-rays penetrate down to. So the gray zone is the zone, that's our answer. That's the zone allowed by pHs. So the top curve is the low PA case, and the bottom curve is the high PA case. And everything else, everything in between is what we think is plausible. So AM is the greater concern. You see it barely pokes its head above 1. Right. And for higher surface densities, it really drops. For comparison, I'm plotting the no PA curve. There were no PAs at all. You can see it's still pretty low. Right? But it's even lower if you include the PAs by order of magnitude or so. And the reason why AM is more important than RE, notice RE, meanwhile, is, for my money, infinite. I'm not going to worry about electrification compared to elevated diffusion. And the reason I don't need to worry, of course, is because the ohmic criterion cares about the fractional electron density. But the ambipolar criterion cares about an absolute ion density. And the higher up you go in these surface layers, the lower the densities are, and the lower the collision rates are. The ambipolar criterion cares about an absolute collision rate. So the higher up you go in these surface layers, the lower the densities are, and the greater the concern is. That's why this curve starts to turn down again at these low surface densities, whereas the Reynolds number shows no sign of abating. So that's qualitatively why it is that I worry a lot about ambipolar diffusion.
But even if you did have Paul, you would right half the time.
Sorry?
Even without Paul, you would
Oh yeah, well there it is. Well, there you're looking at it. That's right. But it's an order of magnitude. In fact, we computed the accretion rates. Is that my next slide? Yeah, pretty much. We computed the accretion rates without PAs, and they're higher than the accretion rates with PAs by about an order of magnitude, just to address your question. Okay, so how do we translate this into accretion rates? Well, this is where this work by Stranding By has been really great. His paper is just submitted. He lent us an advanced copy, and he can translate an AM into an alpha. Right? I give him an AM, he gives me a Shapiro-Semyon alpha. And the way it works is there's this relation relating alpha to the plasma beta. This was known for a while. This was known back in 95 in many studies. The fact that the stress is proportional to 1 over beta, with beta as the plasma beta, that's, in retrospect, I suppose, not too surprising because it's just telling you that BRB5 is on the order of B squared, which it would be if the field is pretty tangled. turbulent in origin, right? That's essentially what this statement is saying. BRB5, the Maxwell stress that goes into the alpha, is on the order of the total of the square. That would be the case if the field is highly fluctuating. So that's that result. There's also this result, though, which is from Schrening-Bai, which is saying that, well, I need to know beta, right? What is the saturated value of the plasma beta when the MRI is fully saturated, when it's fully going? And there is no unique answer for beta. Right? It depends on the geometry of the field that people assume, the seed field, and it also depends upon the strength of the seed field that people assume. Nevertheless, if you scan over parameter space, you can find a minimum beta, right? Sort of the most optimistic conditions for the MRI to operate. In other words, a minimum beta or a maximum alpha in the saturated state. And that's this curve, this beta min as a function of AM. That's this curve right here. So beta min as a function of AM. Beta could be anywhere in this zone, but the minimum beta is given by this curve. Okay, so we're going to be optimistic. We're going to say things are most conducive for the MRI. See how far that gets us. We calculate an alpha max for an AM. He gives us this relation. We compute with our chemistry code this relation. AM is a function of surface density. And we get an m dot, which is shown here. So m dot versus this radius. And this is the low path curve. This is the high path curve. And here are the observed rates. And it's not doing that great a job, I have to say.
And the no-plot curve?
And the no-plot curve, I haven't plotted. The referee insisted that we plot this. So the high plot, I forgot to plot on this plot. It sits about an order of magnitude above, so roughly like this. Okay? I think the no-plot curve is silly because plots are observed, so I'm not going to deny there. You see the emission line. So there it is. Okay, so that's the result. All right, X-rays plus pos, and this is just the things that you can see, right? These are just possibly to observe. Who knows what kind of junk is inside these disk surface layers? These tiny little grains that are not observable, soaking up all your charge. Who knows what junk is in there, ruining your answer?
Is part necessarily much more important than grains of the fraction of
Our as far as micron size grains go, right? Those are people have some feeling for the abundance of micron size grains, and it's positive way more important. Orders of magnitude important.
Because in terms of mass, part has zero mass. Right?
Exactly, but in terms of, you don't care about the mass. You care about more. You care more about the surface area.
Well, there's uncool focusing on.
Yeah. So, I mean, the short answer to your question is we include the grains too, right? I mean, that's this plot right there, right? So we've got plenty of grains going on according to what people think of the abundances are and so forth. And yeah, they're charged by, up to -22, whereas the pods are only charged to -1, but there's just so few of them that they don't make any difference compared to the pods. It's a small dimension animal.
Did you get the paw-like features from the paw-like things stuck on the big grain? It doesn't have as much surface area. You need that much surface area to take these things.
Oh, yeah. I mean, what you're really seeing, right, are the CC and CH lines of emission. So I suppose if a pod is hanging off the end of the grain.
But you calculate the abundance based on the numbers.
Yeah.
So it doesn't matter.
It doesn't matter.
You can
Yeah.
stick that in there, you should be happy. They collect one constant.
Yeah.
Well, but if they are little hairs in one big ball,
They
they're
still have
much
the
less.
same area.
They're much less necessary than
No,
just
so they won't
individual.
face the image. You're only absorbing.
Yeah, so there's emission necessary.
That's what it's tiny.
How grains interact, how free electrons interact with pods that happen to be hanging on the edge. I would have guessed that it wouldn't make any difference if it was hanging off the edge, but I haven't done any calculations.
You could get enough surface area.
So-
Let me ask you though what you're sort of going after here. Are you going after pods in the supposedly ionized layers out at 10 AU, or are you worried about the ones in the hole? Yes,
Oh,
or
this,
both?
right. So this calculation is for conventional disk. It's in the surface layers. I'll show you at the very end applications for transitional disk. But so far, this is just conventional. Yeah, this is just the plain Jane. Okay. So I've been pretty excited about another source of ionization, one that's sort of obvious in retrospect, but nobody talks about it, and it's UV ionization. Far UV, though, and I can never remember what the far refers to. And now I can. I worked on it for a few months. So far refers to the fact that it's actually not as far as extreme UV. So I'm not talking about the extreme UV. I'm not talking about the photons that are shortward of 912 angstroms. Because all that radiation, the line continuum photons, they get stuck ionizing hydrogen way up in the high atmosphere of the disk. The density is just way too low. It's fully ionized, but I don't care because there's just way too little mass there. I care about the photons that are longward of 912 angstroms. They don't interact, well, they don't ionize hydrogen, but they can ionize trace elements like carbon and sulfur, which are fairly cosmically abundant and tend not to be depleted onto rings, at least in the diffuse ionizing rings. So for the far UV photons, you get plenty of ionization from carbon and sulfur. There's a complication for carbon. It happens that FUV photons that can ionize carbon can also dissociate H2, so you need to worry about the shielding of the carbon from the H2. You can do all that. Sulfur doesn't have this problem. There's a nice 100 angstrom band pass. That's just sulfur's domain. Very nice. And there's plenty of FUV to go around, and these are observations of the FUV radiation from two stars, GW Hydra and BP Tau. They're accreting stars. The FUV is supposed to be coming from accretion shock, maybe also from a corona. I just care that you can measure the total fluxes. So in this pass band, the one I'm interested in, between 912 and 1200 angstroms, this pass band right here, yeah, a lot of it is in the lines, but there's also a continuum. You can account for the lines too. It's just an extra detail to account for in your source vector. But it's easier just to do the continuum. The continuum has a luminosity of about 10 to the 30 ergs per second for T-Tauri stars. And for hotter Herbig AEs, you can get all the way up to 10 to 32 ergs per second just from black line. So plenty of energy to go around. And what can I say? So how far does the FUV penetrate? It won't penetrate as far as the X-rays, because the cross-sections are a lot higher. You can estimate on the back of an envelope how far they'll go. You do a little strong brain calculation. So you balance the rate of photoionizations with the rate of recombinations. If you want to estimate the electron density or the ion density, it's just from carbon 2, right? Or sulfur 2. That's just, it's completely ionized. So you just use whatever abundance you're going to assume. If it's cosmic abundance, it's 10 to the minus 5.
So dust
For sulfur.
Dust absorption doesn't matter.
Dust absorption does matter. And all my results will be low cases of high dust absorption and cases of low dust. It does matter. I'll show you, the next slide should have it. But the dust doesn't matter in the usual way that people worry about, which is charge recombination. Because these electron fractions, these electron densities, I mean, it's F, right? Is 10 to the minus 4, 10 to the minus 5. And that's orders of magnitude larger than even the pH abundances. You can throw all the pH if you want in there. It won't make any difference. Because there's just so many electrons given to you by carbon and sulfur. I should point out, there is some information about the carbon abundance, at least. Herschel measured this 158 micron line from carbon 2, right? This famous cooling line in the ISM. They get moving in these disks. And it's optically thick, unfortunately. It's consistent with cosmic abundance, but because it's optically thick, it's also consistent with an abundance that's about 1/30th that of cosmic. So we'll play with that. In fact, it helps to have it a little bit depleted, because you can see that if you do this little calculation, you'll find that the slag that you ionize actually increases, of course, with decreasing abundance, right? Sigma active layer goes as 1 over F. That's because the fewer things you have to ionize, the easier it is for the FUV radiation to penetrate through your disk. So it actually helps to have some depletion. Okay, here's the same plots again, RE and AM. So black curve is a dust, so your, Chris, this is to address your question. The black curve is for a relatively dusty model, and the blue curve is a relatively dust-free model, okay? And the dust-free ones, you extend the AM and the RE out to larger surface densities by about a factor of 10 in the range of parameter space. So you're talking about an active layer which can range anywhere from 1/100th of a gram per square centimeter to 1/10th of a gram per square centimeter. And I know that doesn't sound like a lot, but it's completely the ideal image to limit. No ambipolar diffusion, no Hall effect. It's just textbook MRI. And it's that thick, okay, up to 1/10th of a gram per square centimeter. And can it buy you enough accretion rate? That's the question. So these two peaks, by the way, this is the carbon front, and that's the sulfur front. That's explained that the Hall effect is not important. And here's the bottom line. So m dot versus this radius again. Here's that same X-ray plus PA case. And here's my FUV band, right? Put all the dust in you want. Well, it matters insofar as this is the dust D case, and this is the dust free case. It's absorption now, right? Not charge recombination, but just good old plain optical depth effects. And you're doing better. At 10 AU, you can get between 10 to the minus 9 and 10 to the minus 8 solar masses per year. At the outer disk, I don't think there's much of an issue. MRI can work. It's still the inner disk where this layer is just too thin, unfortunately, to sustain that flux. But we're limiting the problem now, right? It's some progress. The problem now is explaining how do you sustain the transport of 10 to the minus 8 solar masses per year from 10 AU down through the 1 AU region. At the 10th of an AU, it's getting hot enough that thermal ionization can come back again and save the day. So it's really only this last decade in the vicinity of 1 AU where I would really like to know what is sustaining the accretion. We have one hope, and that is, all these chemistry calculations we're doing neglects turbulent mixing of the plasma down to deeper layers. And that will help extend the MRI active region. It would only help, though, if the turbulent mixing times are short compared to the recombination times, the ion recombination times. So you'd like this recombination time to be long compared to the mixing time. We'll just use the canonical time for simplicity. And these are our rough estimates. It's not that much longer, but it is something to think about. On the face of it, maybe this is just an order unity effect, in which case it's not so interesting. But maybe there's a way to make this run away. In other words, you mix the plasma down to deeper, closer to the midplane. You'll reduce the electron density as you mix it down and dilute it. And that'll increase the recombination times. So this way you can help your way along down towards the midplane. You keep extending the recombination time, longer and longer, to mix your way down further. Maybe that's the case. It's something that Daniel is exploring right now.
If you assume that was the case, would you meet the criterion for that MRI all the way down?
You have some room, right? Because there is enough room to play with because the ambipolar numbers are like 1,000. So you have about 2 orders of magnitude before the MRI criteria comes down to data. So there is space to breathe. Yeah. Okay, here's my last slide. So applying it now to transitional systems. So transitional systems have an extra surface layer here at the rim. And the accretion rate from this exposed rim is actually comparable, maybe not too surprising, to the accretion rates that are just outside the rim. You account for this extra accretion rate. You plot it versus the rim size. You get this FUV band. Again, X-rays sits below. And now I can plot some more data. I plot the data of for transitional disks, m dot for transitional disks versus the hole size. The reason why it trends like this, according to the theory, is just because the bigger the hole, the more the surface area is exposed to the FUV radiation, and the more material you pull off the rim. So I was encouraged by, we slapped on the data, and I was encouraged by this. There's still a problem of transporting all of this accretion at small radius. That problem is still there. But at least in the transitional systems, you might be able to invoke companions to help shuttle the material along closer onto the central star. So that's my talk. My bottom line is that FUV ionization is really, I think, the king of all ionization sources. And it's not subject to all of these nasty caveats about how many small grains there are absorbing all these charges. It's very refreshing, I have to say, that it's an ideal image to limit all these non-ideal effects that people have been obsessing about. For the FUV layer, they just go away. So that's my talk. Thanks.
We have time for maybe one or two questions.
Mark?
So, actually, it's independent specifically of your model, but if the accretion would ever stop, your layer disappears, your accretion disappears, and so you're sort of getting to a state where the whole star is not accreting anymore. So it's sort of an unstable accreting state you're in. Like you should stop accreting, you don't have FUV anymore, so you don't have ionization.
Well, maybe not, because some portion of the FUV is thought to arise from magnetic stellar activity.
Okay, yeah, that's
some portion of it is coming from that.
So the other thing FUV can do is to strike electrons out of grains.
Right.
So even if the opposite does, which blocks all FUV from the carbon and sulfur atom, would that contribute self-ionization to the
It's something that we haven't included at all. We really should, because I get that question all the time. Which is ionization of the grain itself, photoelectric effect.
Right.
But on the face of it, you're adding more electrons to the system. So at least in the FUV layer, I would imagine you can only help. But
maybe we combine back with grain too fast, but I don't know.
yeah, I don't have much of a feeling.
So your basic point was that there's so many more electrons from these fairly abundant carbon and sulfur.
Right.
Because you have one electron per carbon, and you only have 20 electrons per grain, they have a hell of a lot of carbon. Right? So you don't, you just won't charge up to 20 electrons per carbon. Right? There's a lot better charge to mass ratio per atom to increase your grain.
Yeah, my guess is, I think what you're saying, my guess is that there's just so much carbon and sulfur around at a 10 kilograms per centimeter that you're just awash with carbon 2 and sulfur 2 and electrons. And if you add some grains to the mix, it's...
I mean, the only thing, the only reason is in dust diffusion is after that, FUV is providing mostly out of grains.
Well, but that in one case, at least one of his plots, that set is effective, right? That was the dust.
Where's the dusty versus
the dust,
dusty versus dust-free?
That goes back to Chris's question. Just block out all the UV, dust, so it can't get much farther.
Well, but if you really use the output that, well, I thought you sigma goes down to like 10 - 3 or so, right?
10 minus 2.
It's only factor 10.
It's only factor of 10.
That's the
It's a factor of 10. I mean, that factor of 10 is this factor of 10 right here. This is the dust E, and this is the dust free. Or dust, there's still dust, it's just less. Okay, so that's what this zone is nothing to do with pH. This is everything to do with pH. This is nothing to do with pH. This is everything to do with just absorption.
So but that's the using ISM grain size or something? Or?
I don't care, actually. That's the beauty of it. I just care. No, exactly. But I don't have. I just use a proxy. I just say there's some column of gas that produces optical depth unity in the FUV, and that ranges from 10 to the 22 to 10 to the 24. Now recall, ISM is 10 to the 21, and the best estimates based on all this SED modeling that I used to do too, based on the dust settling, 10 tell you that dust is depleted relative to gas by factors of 1 to 1,000. So that takes 10 to the 21 to 10 to the 22 to 10 to the 24. So I'm using 10 to the 22 to 10 to the 24 in making this clock. Yeah.
So if we ignore what we know to be happening at the start and think about forward modeling what would happen to the FUV-dominated MRIs, you have a radius, you have a trend of m dot max versus radius, which is lower at smaller radii.
Yeah.
So you supply in matter that the
Right.
interdisk can't transport. What's the long-term evolution of that?
Well,
And the amount is comparable to the
sure,
current mass, right?
sure. Well, I mean, here's just one scenario, okay? Builds up in the inner disk, and you just keep letting it go. What are your options? It becomes gravitationally unstable. And maybe it transports, and maybe gravitational force take over and transport the rest of the way. That is one scenario.
Is that possible?
There's no, as far as I can see, observational constraint against it. What do we really know about the surface density of material inside of 1AU? Nothing. We just know it's on the thing.
We have some detections for gas.
Surface layer.
It's just the surface layer. But in the transition disk, they're relatively thin, so it's also.
Even for transitional disks, I showed you the CO emission.
Yeah.
It's all this warm CO sitting on top.
How do you know sitting on top makes the transition disk go?
Oh, no, you're right. No, you're right. Yeah, you're right. All you know is that the surface density is greater than 10